Hello everyone, welcome to today's ConSteel webinar. Today's topic is the new feature of the brand new ConSteel 10 and csJoint 10. Today's webinar will be presented by Roland Doka and me, András Herbai. Just some practical information. Control panel can be hid with the red arrow button, and the questions or messages can be sent with the chat options. At the end of the webinar, we will answer them. Today's webinar is about the new feature of the ConSteel 10 and csJoint 10. The latest version of our structural analysis and design software was published at the beginning of April. At first, I will shortly talk about some significant system improvements. Then Roland will introduce the new special freeform package. After that, we will present the structural input functions, for example, the new DXF and global RSTUB and SAP 2000 complex model import, and the awaited structural grid, and some minor development such as hot-rolled, hunch, and multiple support. Then I will present the new adjustable color legend for surface analysis result. Then Roland will present one of our new design tool, the stable length design. After that, I will show you the new reinforcement calculations for slab according to the Eurocode 2. Then I will demonstrate the new functions of csJoint 10, and finally I will introduce the new Tekla structures, import and export functionalities. Let's see the performance system improvements. ConSteel and csJoint finally moved to 64 4-bit. Thanks to the new technology, ConSteel and csJoint able to utilize more than 3 GB memory. Therefore, bigger and more complex model can be built in our software. And ConSteel able to connect with other 64-bit software, for example, Tekla structures. And what else? The following operations were speeded up. Model loading, creating or modifying graphical objects, selecting many objects, diagnostics, creating analysis results, diagrams, standard verifications, database, and finite element model generations. So these are the system improvements in ConSteel 10, and at this point I would like to ask Roland to take over the presentation and introduce the new freeform package and the stable length design in ConSteel 10.
So welcome everybody, my name is Roland Doka, and as my colleague András said, I'm going to show you some new functions like the improved import functions. I'm going to start with this one. In ConSteel 10 we have some new, not new, but developed and improved import functions such as DXF importation, a brand new global and SAP import functions, and we also made improvements in the importation and the exportation from and to Tekla structures. I'm going to start with the global and SAP import functions because they are work the same. From these softwares we can import an XLSX file format, which is a table form basically. I can show you how it works. So this is an exported model from Global to an XLS table form. In this table, the model parameters are stored in different worksheets. So, for example, the member loads for different load cases are stored in different worksheets, but every cross-section or member eccentricities, member releases are separated to worksheets. And if I go back to ConSteel and choose the imports from Global or SAP, as I said, they work the same, and select the function, we have this import dialog where we have to give the file on our computer, this table, this XLSX file. So okay, so this is the file. We opened it. Now we have to set the unit of the model, which can be millimeter, centimeter, or meters. This is basically the dimension that we were used in the other software, Global or SAP. Right now I'm going to choose the meter, and also we have to set the direction of model z-axis that we were used in Global or SAP. I used the -z direction, and here we can check that what kind of objects can we and do we want to export into ConSteel. So, for example, cross-sections, nodal supports, load cases, nodal forces, concentrated forces on members, and member forces can be imported. If you don't have any of these objects in your export file, you have to unbox this checkbox. So right now I don't have nodal forces and concentrated forces on members. Okay, but if I have these settings and click the OK button, the importation process will be initiated, and as the next step we get the section and material import manager dialog, where we have to choose that the sections that we were used in the other software should appear in ConSteel. So this is basically a section conversion and also a material conversion between the two software. If you click OK, the importation will be performed. And if you have any worksheets that are empty, you get a message, get a notification about it. After you click OK, the model appears in ConSteel, and as you can see, the section is imported. We have release settings imported. We have imported the rotation, the degree of rotation, and also the eccentricities would be imported if we would had any of them. Also, we have imported the load cases and the loads in the load cases. So this was the import from Global and SAP 2000, and I would like to go on with the DXF, with the developed and the improved DXF import function. So I'm going to delete this model, and at the file menu and import tools, we now find this DXF option, and if you click on it, you get two dialogues. One is the Windows opening dialog, where you have to choose your DXF drawing file, and the DXF import dialog itself, where you can set different, where you can do different modifications on the imported DXF model, which is automatically placed in the modeling area. So for example, you can set the unit of the DXF model file with this drop-down menu, scales the model automatically. Okay, but you can set a scale factor manually if you want to, and also you can set a placement of the, you can move the placement of the origo what was used for the DXF model. So if I click this button and click anywhere in the modeling area, the origo of this DXF model will move to that point. Also, I can choose the plane of the placement of this DXF file. I can use user coordinate system if that is preferred, and also we have layer functions at the bottom of the dialog. We can choose if we want to use the layers of the DXF model with its colors, and these imported DXF layers will be represented also here in ConSteel at the Layers tab later. But now I'm going to use the ConSteel layers, and if you click OK, this DXF will be placed in the modeling area. Okay, so that was the DXF import function, but I would like to link this with the freeform package, with the representation of the freeform package. So for this freeform package, let's assign some cross sections to these lines of the DXF model file. So I go to the Structural Members tab, I quickly apply some welded box cross-section. And apply to the DXF lines. Okay, it's done. The next step is to place some supports, for which a very useful function. It was not developed for ConSteel 10, but already in ConSteel 9, the multiple placing of joints. So I choose this function, and I will assign the supports to the model. Okay, so we are ready with the sections and the supports. As you can see, we have to make some modifications, because right now all of our box sections are aligned to the global z-axis. So first I'm going to rotate these sections perpendicularly to the surface, to this surface of the building, globally all at once. This is the first function of this freeform package, what was missed by more users. So how to do this? You have to choose the local coordinate system settings here at the Structural Members tab. You have to click on it, and you have to choose this beam function, and then select all of the beams. And using this function, set the z-axis perpendicular to the surface formed by the connecting beams. all of the bar members' local z-axis will be aligned perpendicularly to the surface of this structure. Okay, the next step is about loads. I mean the next function is about loads and surface loads exactly. So let's go to the Loads tab, and the new function is a load transfer surface function. So click on the load transfer surface button, and this is a new function, the multiple placement of load transfer surfaces. This is used to cover free-form structures pretty easily and in a quick way. So for example, with a simple selection you can create these load transfer surfaces on the structure. And I'm going to cover the whole building with it. One more important thing to know, that currently the maximum number of the selectable edges is limited to 200 edges. So for example, if you want to select a pretty large area in the model containing more than 200 edges, the program will not note you that the maximum number is only 200. You can roll one load transfer surface onto another, because it won't multiplicate them, so it's pretty easy to use and speeds up the process of this covering, even with the limitation. Okay, we have some duplications which has to be deleted, but later we are going to fix these little problems in this function. So as I mentioned, one way to draw load transfer surface with this function is to select with the rectangle, but if you select with the click, select the edges with click keys, simple clicks, it will be drawn too. Okay, so we have our load transfer surfaces. We could apply loads on it, but let's try it out. I will place surface loads assigned to the local coordinate systems of the load transfer surfaces, but as you can see, these loads are not aligned correctly, and this is because every local z coordinate system of these load transfer surfaces are aligned inwards or outwards the building. So for example, if we check one, for example the z-axis is aligned outwards the building, but this is aligned inwards the building, and this is not good. You have to make some modifications before placing the loads, and to do this we have a new function. I want to delete the surface loads. Okay, so at the structural members tab, and again at the local coordinate system settings, we can do the modification So click on the function, select the plate option here, select the surface like the information says, and then we have this icon here, the set z-axis by point. So if you click on this function, you can define a point where should the z-axis aligned on the load transfer surfaces. So if you click inside the building, all of the z-axis will be turned inwards the building, and if you click this button here, the invert z-axis, all of them are going to align outwards the building. This was the new function, this set axis by z-axis by a point, and yeah, basically these functions were the freeform functions, and from here you can continue with the regular drawing and modeling functions. So I can simply place loads on the structure and continue on with the design. Okay, that was the freeform and import functions what I would like to present. The next one is the stable length check, but I have to open a new model again for it. So this stable length check can be used for plastic design to verify the stability of a bar member. This check is based on the results of the plastic hinge analysis, what was developed in ConSteel 9, and another key function for this stable length check is the frame corner wizard, which was also developed for ConSteel 9, and we have webinars on our official YouTube channel which are presenting these functions, the frame corner wizard and the plastic analysis too. But right now I have brought a model. It is a 3-bay Hunched frame. I have modeled the restraining effects of the purlins with these lateral restraints. I have haunches on the beams, and I have applied the frame corner on the structure, which is essential for this stable length check. I have also applied loads on the structure, and I have not run analysis, but I will run a plastic analysis, second order analysis with buckling analysis too. And after the analysis, we see the results. First, the second order results. In the second order results, we can see 3 formed plastic hinges. These plastic hinges are below the design load level of 1, but if we check on the plastic hinge history, we see that we have right now 4 plastic hinges. The first is developed at the design load level of 0.8. The second, and on the column below the haunch. The second one is formed on the beam at the end of the haunched section at the design load level of 0.9. Oh, sorry, this was the third. But the second and the third are almost the same. They are both on the end of the haunched segment. the fourth plastic hinge is on the beam at the maximum bending moment point. This is over the design load level, so we will take only into consideration the first three which are below the design load level of 1. If you are interested in plastic analysis design, please check out our webinar in this topic on our official YouTube channel. Let's go on and continue with the stable length design itself at the Global Checks tab. The appendix BB3 of Eurocode says that I can show you here, that the lateral torsional buckling effects may be ignored where the length of the segment of a member between the restraint section at the plastic hinge location and the adjacent lateral restraint is not greater than a stable length, where this stable length is calculated with this formula. And also says that here, that this lateral torsional buckling effect may be ignored where the length of the segment of a member between the restraint section at the plastic hinge location and the adjacent torsional restraint subject to a constant moment is not greater than the stable length, which is calculated with this formula, or depending on the moment on the structure, with this formula. But basically we have two types of stable lengths calculated, one between the plastic hinge and the nearest lateral restraint, and the other is between the plastic hinge and the nearest torsional restraint. So we have a formed plastic hinge here. We have a lateral restraint, for example the purlins. This is one kind of stable length between the lateral restraints, and here we have a torsional restraint. So the other kind of stable length will be the stable length calculated for this segment between the torsional restraint and the plastic hinge itself. So we will calculate these stable lengths in ConSteel, and this is what I'm going to show you. So click on the design dialog, check in the buckling check, and click on the calculate button. And as you can see, we have high utilizations, over 200%. Here at the top of the window, we have a new option for the result view, the stable length check. And if you click it, you basically see you can see the plastic segments in the region of the plastic hinges, and these are highlighted with these colors. So these are the plastic segments. The black segments will be checked elastically. Only these segments will be calculated and taken into consideration for this stable length check. How this stable length check works is the following. First, ConSteel recognizes the place of the plastic hinge. So we had 3 plastic hinges. The first one here at the top of the column, here at the haunch on the beam, and here at the other beam. So at the first step, it recognizes that where is the plastic hinge, and it starts to move. The program will check and start to move in one direction and the other direction from that plastic hinge. In case of this column, of course, only one direction, and it will search for lateral or torsional restraints. I mean lateral and torsional restraints too. And if it finds one, for example, this restraint of a purlin, it will stop, calculate a stable length for this plastic segment between the two lateral restraints, and compare this stable length with the length of this segment itself. And if the calculated stable length is higher than the length of this segment, the calculation will says that this section is adequate, or if it's lower, it will result in high utilization. So let's see the calculation details. Click on this utilization and click on calculate section, which will bring up the CS section module. And let's see the results, where we have a new option, the plastic stable length check. And as you can see, at the results, we have these two kind of stable lengths: the stable length between the lateral restraints and the stable length between the torsional restraints. Open it up, and you can see the utilization, the case of this calculation, and also all of the necessary parameters for this formula that you may saw at the standard. But the most important thing, that we have this length between restraints and the stable length, the calculated stable length, which is now 0.88 meters, and it is lower than the distance between the lateral restraints, and this results this high utilization. So we have to change the layout of the restraints, and we have to reach the distance for the supports to go below this 0.88 meters. Okay, and also we have here the stable length between torsional restraints, which is not the dominant formula right now. The length between the torsional restraints are also the same now, 1.93 meters for this plastic segment, and it is adequate. So this is what we have to solve now. We have to go below 0.88 meters, and we are going to do this. We will go back to the structural members tab. We will choose the point support function, and we will define with this new multiple support placement function a lateral restraint to the top flange of the beam. So we will choose the Y direction, and we will choose the top flange of the beam, and this new function is able to receive data like this. So I can place multiple support in different distances. So I type 1000 millimeters, click on this beam, and program will place this support, counted this 1000 millimeters from here on the beam, and place the support. Okay, and what are the distances right now? So as you may saw, and I hope you remember, that the distance between the lateral restraint and the plastic hinge was 1.93 meters, and the stable length was 0.88 meters, which is now reduced to 800 millimeters. So I managed to go below that value. Let's check the results, run an analysis again, and also a global check, and switch to see the stable length check results. And yes, as you can see, we are below that critical stable length 0.88 meters. So right now the cross-section is adequate here, but not adequate here. What is the problem here? We can check it easily by clicking it and calculate section. The problem is again the distance between the lateral restraints, because the distance between the purlins, which are the distance between the lateral restraints, are now 2 meters and 20 centimeters, and the stable length is 2 meters, nearly 2 meters. So we have to go below this value. And one more thing I would like to show, that these two cases were both stable lengths calculated between lateral restraints, but as you can see, this is the end of a plastic segment, but there are no lateral and nor torsional restraints can be found here. Why this plastic segments end here? This is because if you check on the analysis result, and also if you bring up the calculate section function, you can see that the calculated stable length for this section is a torsional, between the torsional restraints, and you can find no torsional restraints here physically. But if you go back to the analysis tab and check the second order results and the bending moment of this on this beam, you can see that a bending moment 0 point is just right here, which acts like a torsional restraint on the structure, and this is why this plastic segment ends up here. But this is adequate, so we don't have to make modifications now. We have to only deal with this section, which is about the distance between the lateral restraints, which is going to be reduced quickly with also the new multiple support placement function. I will select the Y direction supports, which are already placed with this new multiple support placement function. And if you check in the object property here, you can see that these supports are defined in an interesting way. The first 1800 value means that the first support is counted here to here with this value, and from that point 5 times the 2200 millimeters value is measured. So if you modify this value to, for example, 1800, it will modify all the supports on all beams. So this is a very quick method to modify the layout of the supports. Okay, let's rerun the analysis and check the results for the stable length check. And now, as you should see, we have no utilizations over 100 now. All of our plastic segments are adequate, and we could continue with the elastic design for global stability resistance, because the elastic parts are still not adequate, but this should work as usual as in ConSteel 9 and previous versions with the general method of Eurocode. So this was the stable length check design. I would like to give back the presentation to my colleague András, and thank you for your attention.
Okay, thank you, Roland. Let's continue with the long-awaited structural grid function. To introduce the new function, I have created a multi-story building. I'm just closing not necessary models. Okay. So I have created a multi-story building to introduce the structural grid function. So the structural grid function can be found on the Geometry tab, and the last button is the structural grid functions. With these functions, multiple grid can be handled parallel. New grid can be created with the blue plus button. Parameters of the new grid can be set in the structural grid properties field. This is the first field. Division can be set in X and Y direction. In default, the X and Y directions are parallel with the global X and Y axis, but the grid can be rotated if it's necessary. The divisions between each of the grids can be set separately. So here we can write the distance between the grid lines. With the new button, we can add some new rows. Or if the divisions are uniform, we can set with a simple multiplication factors. So now in my current example, in the Y direction, the first division is, for example, 5,000 millimeter. The next two dimension is 6,000 millimeter, so it's 2 times 6,000 millimeter, and the last one is, I create a new line with the new button, so the last one is 5,500 millimeters. Okay. In the Y direction, the first three is uniform, so it's 3 times 5,000 millimeters, and the last one is, the last one is 2 times 4,500 millimeters. Okay. The next property is the caption properties. Caption can be placed at the start, at the end, or both of the end and the start point of the grid line. Separate settings can be set to the X and in the Y directions. Type of the caption can be also set. It could be a number, a capital or a normal letter, or it could be a Roman number. Now in the X direction, I set the numbering. In the Y direction, I select the capital letters. If it's necessary, initial value or prefix can be set for the numbering. Overhang of the display lines can be set if necessary. Now I'm set 2000 millimeters, and color of the grid line also can be set. And finally, the ordering of the numbering can be set. Numbering can be ascending or descending from the origin of the structural grid. And the last parameter field is the position of the raster. Position of the raster can be set by coordinates in the global coordinate system, or by a simple click with the black arrow button. Now I select the left bottom corner of my building, but it's in the origin of the global coordinate system. Okay. Here we can define the rotation of the grid if it's necessary in the XY plane. And the last parameter is the level of the grid. It can be placed on a given level or with the checkbox option. So with this checkbox option, the grid can be follow the visible story if stories are created. And the end of the settings with the apply button or with the create button, we can place the structural grid on the model. Okay. Structural grid, place structural grid can be modified easily. All of the parameters can be modified with the apply button or with the modify button. You can modify the created structural grid, and with the checkbox, if it's necessary, we can switch on and switch off the placed structural grid. And now let's see how can we add another structural grid. With the new structural grid button, we can create a new one. Of course, different division can be set with the division properties. In the division field, with the up and down arrows, we can move every given division to up and down if it's necessary, or with the red X button, we can delete the selected row. Okay, so let's set another structural grid in the Y direction. The first division is same, it's 5000 millimeter, but the next one is 3 times 5500. In the Y direction, it's okay. And now I'm positioning the new grid with a simple click to the right upper corner of the building, and with the apply button or with the green stick button, we can place the new structural grid on the model. Okay, so, and if it's necessary, we can give initial value in X and in the Y direction. For example, in the X direction, I set the initial value as 5, and in the Y direction, I set G. And with the OK button, we can modify the place structural grid. And now if I switch on or switch off one of the previously created level, you can see the structural grid, the place structural grid is follow the visible stories or model portions. Okay. Some minor new structural input developments in ConSteel 10. If you open on the structural member tabs the section administration and open and load sections from library, you can find the new steel cross sections section bank. This is the British steel section catalog, and if you go back to the macro section, in the welded front plate macro sections, you can find 2 types new macro sections. The first one is the slant flange welded I or H section, and the second one is the welded C connections. Okay, so let's continue with the adjustable color legend for surface analysis and design result. So for this, I open a surface model. So until now, for surface analysis results, only continuous color legend visualization can be used. In case of buckling, it is very spectacular, but in some other cases, for example, stress analysis, discrete color legend is much more useful. So now in ConSteel 10, not just contours, not just normal contour surface available, but discrete color legends also available. So in ConSteel 10, the color legend visualization was improved. Some new developments for the normal contour surface visualization. If you click with right mouse button on the color legend, we can modify the maximum and the minimum values which come from the model, if it's necessary. So, for example, if I go to the stresses, for minimum I can set, for example, 235 as a minimum value to the visualization. Here we can sum. How is it look like? With the reset button, we can set the original automatic panel again if it's necessary, and if it's necessary, we can save the created palette settings, and we can open it later. Or with this checkbox, we can set as a default these settings for this kind of result visualization. Okay, let's see how does it look like with the new discrete colors visualization. In the fourth drop-down menu, you can select the discrete colors visualizations. And if you click with the right mouse button on the color legend, the new dialog is open with lots of new settings. First of all, we can set the levels of the legend with the up and the down button. With the apply button, of course, we can use the new settings. We can reset the automatic palette if it's necessary. And also we can save the created settings for later use, and from the drop-down menu we can select one of the previously created, and also we can set as a default palette for this kind of result visualization. If it's necessary, all of the value can be modified manually. For example, modified one of them, and in this case ConSteel interpolate between the given values. Okay, with the yellow button near the modified values, we can go back to the original value, or if it's necessary, with the small red bin button, we can delete the selected level from the legend if it's necessary. Okay. So this was the new color legend visualization in ConSteel 10. And the next new function is the reinforcement calculation for slabs according to the Eurocode 2. For this, let's go back to the multi-story building, and let's see how we can determine the necessary reinforcement in slabs. So I have previously created a multi-story building with 3 concrete slabs. Concrete slabs can be created with the plate function on the structural member tab. And if case of concrete material, a new option is appeared on the dialog. We can set the reinforcement, and with the 3-dot button we can create a reinforcement for the slab on this new dialog. On the dialog we can set the diameter of the reinforcement in the X and in the Y direction, and on the top and on the bottom of the slab. And also we can set the material grades of the rebars also. the X, and then the Y direction is the local axis of the slab. We can set also the direction of the main rebar with this radian button. These directions rebars will be the outside. So, for example, in this settings, the X direction rebars will be outside in the slab, and we can set the covering from the edge of the slab to the outside of the rebars. Okay. Several reinforcement can be saved and applied, and from the drop-down menu we can select the used one. Okay. Reinforcement parameters can be modified if we select the slab, and in the property area with the 3-dot button we can modify all of the parameters. So now I have previously run the analysis, so we can forward to the global check tab where the design, the concrete slab design can be run. If you click on the blue arrow button, the usual design dialog is appeared with a small modification. Because of the huge size of the dialog, the design fields can be opened and closed with this small plus and the minus button. But ConSteel automatically open the dialog with the relevant design fields. For example, in this case, the steel design and the slab reinforcement is opened. Composite column, because our model our model doesn't contain any composite column members, it's closed. Okay. In this case, we can run steel design and slab reinforcement design, which can be found on the bottom of the dialog. So now it's checked. We can select the model portion if it's necessary. Now I run the calculation for the whole model. With the calculation button, all of the selected checks will be performed. Okay. So now in the graphical area we can see the steel design, but with the drop-down menu we can select another results visualizations. For example, here we can see the slab reinforcement calculations. We can see the top reinforcement calculation in the X and in the Y direction, and we can see the bottom calculation also in the X and in the Y direction. Okay. In case of reinforcement design, we use the discrete color legend visualization, and in this case, in the color legend, we can see two informations about the calculations. The first one is the necessary reinforcement in the selected direction in square millimeter per meter, and the second one is the necessary distance between the rebars with the previous selected diameters. For example, it's 8 millimeters. So here you can see the selected rebars. Oh, sorry. With the right mouse button, we can open the color legend option dialog. In case of reinforcement design, we can find new extra options. Color legend can be set not just with the reinforcement area, but the distance also, and you can switch between two options. Now I'm set the scale divisions for 3. And I give the visualizations with reinforcement distance. So now, for example, the first one is 50 millimeters, the second one could be 100 millimeters, and the last one could be 200 millimeters. In the apply button, you can modify the visualization. Okay, and here we can see the calculations where bigger or smaller distance are needed. The visualization is shown with cross hatch. You can see it is under of the given value, and in case of red hatch, it is upper than the given maximum value. Okay, so currently this is the slab reinforcement design in ConSteel. Of course, we will continuously develop this part of the software. So if you have any idea, please do not hesitate to send us your ideas. Okay. The next thing is that we have three new national annexes in ConSteel. So if you click on the standards button, we can open the standard dialog, and here we can see the three new national annexes. The first one is the Cyprian, the next one is the UK national annexes, and the last one is the Romanian national annexes. Okay. So now I'm close these models, and I'm continuous with the following topic, which is the Tekla structures import and export functions. Okay. So I mentioned at the beginning of the webinar, ConSteel has moved to 64-bit and now able to communicate with the 64-bit Tekla structures. It is a good news for those who use Tekla structures to export every day. The other thing is that we totally renew the import from Tekla. Up to this time we used the Tekla output file to load the Tekla structure model in ConSteel, but this file did not contain all of the necessary informations and sometimes did not work properly. So from now ConSteel 10 is import the Tekla model through Tekla API. This way allows us to import not just the structural element, but use the defined classes and other properties from Tekla. Let's see how is it working. So I have previously created a model in Tekla structures. If you see the properties, So if you see the properties, a lot of parameters were set to the members. So we can it is on the top of the members. It is rotated, and here you can see the profiles and also classes set it to the member. Now I open a new ConSteel model, a blank ConSteel model. Okay, and if you go to the file import menu, we can find here a new Tekla structures functions. If we click on it, a new dialog is appeared with the following parameters. With the first options, radio buttons, we can select which part of the model should be imported. We can select all of the members, or we can and we can import it just the selected members. Now I select the first one. The second settings is the layers. We can use the layers of the Tekla structures, the Tekla classes, or we can import to the whole Tekla model to one of the selected ConSteel layers. But now I use the previously created Tekla classes as layers in ConSteel. With the import button, we can start the import process. The first step you can see in the information field, we have to pick the reference point in the Tekla structures. So now I go back to the Tekla structures, and with a simple click I select the reference point. And if you go back to ConSteel, the second step is the section and material grade conversation. It is needed because the section name and the material grade depend on the used Tekla environment. So we have to convert the Tekla section and material names to the ConSteel section names and material names. We can use the default conversation file, or we can load a user-defined or modified conversation files if it's needed. With the OK button, we can go forward. And the next step, you can see in the information field of the import dialog, pick the reference point in ConSteel. With a simple click, we can set the reference point. And now the complete model is imported from Tekla, and all of the set parameters also was imported, and ConSteel used the Tekla classes as layer. If you go to the layers, here you can see all of the Tekla classes, and we use the same colors for the members. And if you see the parameters of the members in the parameter field, you can see the eccentricities are automatically set, and also the rotation is also automatically set, and if we have and also the section is loaded, not just from the library, and also the macro sections can be used for the importations. For example, ConSteel automatically created the proper macro sections according to the Tekla import and according to the Tekla model. If I export back the whole model to Tekla, I would like to show a new small development. From now we can place on steel members not just welded but hot-rolled hunch also. So therefore I go to the structural member tabs, and I place a new hot-rolled hunch on the model. So hunch function can be found on the structural member tabs. If you open the functions, we can switch between the hot-rolled and the welded hunch type. Now I select the hot-rolled. In case of hot-rolled, we can select one of the previously loaded sections as the base of the hunch, and also we can set the length of the hunch, and we can set the height of the hunch, the beginning, and then the height of the hunch of the end of the hunch, and also we can set the position of the hunch. It could be the lower part of the member, the upper part, or it can be symmetrically both sides of the member. Now I'm selecting the lower part, and with a simple click, as usual, I place hunches on the model. Okay, and if you select the placed hunch, here you can see the type is hot-rolled and the section is assigned, and if it's necessary we can change to another sections. Okay. Let's go back to the Tekla export. Now I'm placing some joint on the model to see how the Tekla export is working. So now I'm create some joint by model. And now I'm just place back the default joint to the model. Okay. Let's create another one, for example, to the top beam. And select a different type to the other side. Place to the model. Okay, let's select a gusset plate, a joint. Okay, I place back to the global model. It's a simple click, and finally I create a column-based joint, a semi-rigid. That plays back to the model. Okay. Okay, so now I have a structural model in ConSteel with several place joints. Now we can export back the complete model to Tekla structures. So now I go back to Tekla, and now I delete the previously created model, and I now go back to ConSteel, and in ConSteel in the file and export menu, you can find the Tekla structures function. And with these functions, you can export the whole structural model, not just the member, but the placed structural joint also. The first step is to select the relevant part of the structures. Now I'm exporting the whole model back to Tekla. So now I select the whole model. In the information fields, you can see the next step. We have to pick the reference point of the model. So now I select point of the model. The next step is to, and with the export button, we can start the export process to Tekla structures. The next step is to convert back the section name and the material grade to Tekla structures. We can use the conversation files. With the OK button, we can go to the next step, which is pick the reference point in Tekla structures. And go to the Tekla structures and select the reference point. And the export process is starting. And if you see the Tekla model, all of the elements were exported back with the proper materials, and all of the place joints were created with the inbuilt Tekla macros. So now, now you can see, and also not just the member parameters, but the class parameters also exported back to Tekla. You can see the created joints. So ConSteel is automatically created the Hunched connections and the gusset plate connections, automatically created the beam connections. You can see also the base plate connections were exported to Tekla, and also the placed gusset plate connection was exported to Tekla. Okay, so this is the Tekla structure import export functions. The Tekla import export functions have some limitations. These can be found in the user manual. ConSteel 10 user manual will be available soon. So we are referencing it, and you will find on our website. Okay. And the last topic is the what's new in csJoint. So in csJoint you can find some minor new functions and several new connection types. The first new functions is if you create a new joint with the new joint button and select one of the connections to use, near the connection types you can find two information fields about the basic information of the connections. So in the first field you can find the available section type. For example, in this case you can use the I or H sections, and you can in the second field you can find the considered forces in this kind of connections. So if you see in the gazette plate, you can see in case of double plate flange connections, you can see the available sections, available section types. In case of the splice plate connections, here you can see three types of sections is available in this in these connection types. In case of angle brace connections, you can see the basic parameters. Okay, so this is I think a useful new functions or developments in csJoint. The next one is the joint loadings from tables. So up to csJoint 10, joint loadings could be given by manually, or could be loaded from the structural model if the joint is placed. But from csJoint 10, we are able to import the loading from tables with these new buttons. If you click on the new button, and the necessary we can load the loadings from tables to each of the connections in these joints. For example, you can load loadings to the right flange, to the web plane, to the web front middle edge, to the web back middle edge, and to the column below. If it's necessary, we can download, we can open a sample table to use to upload the joint loading. So this is a sample table. In one table, we can add several load combinations, and we can add the different loadings components. So I previously create some tables to import. So I create a different joint loading table to the right flange. Oh, sorry. Okay, another one to the joint load combination to the web front, and to the web back. Okay, name of the load cases can be used same in the table, or we can use the automatic options. In this case, csJoint is automatically naming all of the load combinations. Now I use the name in tables. With the OK button, we can load easily all of the loaded loadings to all of the connections. You can see I have uploaded 10 different load combinations. Here you can see the loadings. Okay, finally let's see the new connection types in csJoint 10. We have a new type of beam splice joint. It is bolted circular flange plate connections. Of course, the available section type is cube. And here you can see the considered connection forces. For cross sections, I select one of the cube, and with the create button, I create the connections. In these connections, if it's necessary, we can use different section size. For example, select different tube sections. On the end plate property, we can set the outer diameter of the end plate, or if it's necessary, we can give a hole to the end plate. And of course, we can set the thickness of the end plate. Okay, we can set the bolt parameters. We can set the number of the bolts. You can see, and of course, we can set the edge distance. This is the distance between the edge of the end plate to the center line of the bolt. Okay. And if it's necessary, stiffeners also can be added to the bolts, to the connections. Okay. The next connection type is a new connection group. This is a column splice connection group. In this group, you can find two different connections. The first one is the bolted circular flange plate connections. It is similar than the beam to beam connections. You can set the same parameters, but of course the calculation behind the connections is different. The next connection type is the column splice connections. In these connections, we can set the parameters of the splice plate, of course. And we can select between two connection type calculations. So in the gap field, you can find the bearing column splice, and we can select to the non-bearing column splice. In case of bearing column splice, the normal force is transferred by the surface of the end of the column section. So in this case, the gap setting is not available. In case of non-bearing column splice, the normal force is transferred by the plate. So in this case, we can define gap between the column if it's necessary. We can use different column sections. So for example, in this case, I use a smaller section size to the upper column. You can see, backing plates is applied in the connections. Okay. The next joint type is the column-based plate connection. So in csJoint 10, the column-based joint was separated to simplify the using and the understanding. So we separate the connections into pinned to semi-rigid base plate connections and into rigid connections with round beam. In case of semi-rigid base plate connections, not just the I or H section available, but tube also, and and of course in pin base plate connection also the tube available. Okay. And the last group is the hollow section joints. We have new types of hollow section joints. The first one is the key and T joint. you can see, where hollow and cube section can be created. And the last one, the last joint types or hollow section joint types is the tension circular flange plate connections. In this case, cube section is available. And the parameters and the settings are the same as beam spice, but of course the calculation behind the connection is different. Okay, so these were the new functions in ConSteel and csJoint 10. I hope this new functionalities is useful for you. I would like to thank you for your attentions. We have recorded the whole webinars, and we will upload to our YouTube channel, so it will be available on our YouTube channel. So if you would like to watch the recording. So I hope you enjoyed and learned a lot in these presentations. So I would like to thank you, your attention, and goodbye.